Hi, I'm Marc Andrei Tabadero, and I'm here to present the concept of angle modulation. So what is angle modulation? It is a type of analog modulation in which the angle sinusoidal reference function or the angular function is varied in accordance with the modulating signal. There are two types of angle modulation, which are frequency modulation or FM and phase modulation or PM. Frequency modulation is a modulation technique where the information signal is analog and the frequency of the carrier is varied proportional to the information signal. While phase modulation, on the other hand, is a modulation technique where the information signal is also analog and the phase of the carrier is varied proportional to the informational signal. So the difference between the two types of angle modulation is the reference point that varied proportional to the information signal, where FM usually varies its frequency while PM varies its phase angle. In addition to that, PM is like an FM but its phase shift is 90 degrees. When comparing the two types of angle modulation to the amplitude modulation, its main difference is the carrier parameter. While AM kept the carrier frequency constant as its carrier amplitude varied, PM and FM kept the carrier amplitude constant as its carrier frequency varied proportional to its information signal. Consider the given equation for PM and FM signal. Since the carrier parameter has been given to them, we can express mathematically as follows. For the frequency modulation, it can be expressed as the modulating signal is equal to V sub C cosine of omega Ct plus small letter m, which represents the FM modulation index, times sine of omega mt. Phase modulation, on the other hand, it is also like an FM signal, but the inside of it has a trigonometric function of cosine, which describes the phase shift of 90 degrees. So let's consider the time domain and frequency domain of each of the modulation. When we look at the time domain and the frequency domain of an FM, the time domain graph shows that there are wideband and narrowband that corresponds to the maximum and minimum peak deviation of the signal. Wideband and narrowband were created as either the maximum or minimum peak deviation of the given FM signal, in which the FM modulation is the indicator whether the wideband or narrowband were maximum or minimum peak deviation. However, when we look at its frequency domain, it has a carrier or peak spectrum, but it has a multiple sidebands, both lower and upper part on it, which indicates significant pairs of sidebands that depends upon the modulation index of the given FM signal. For phase modulation, while the time domain looks like a time domain for the FM signal, but given its definition as phase shift of 90 degrees, the wideband and narrowband were created from the PM signal as approaches to the zero crossing in the time domain graph. But when it comes in terms of frequency domain graph, the PM spectrum is same as the FM spectrum as theoretically expected. So there are parameters that we need to consider both types of angle modulation. So for the FM parameters, there are 5, which are frequency deviation, FM modulation index, deviation ratio, FM percent modulation, and FM bandwidth. So the first parameter that we need to consider is the frequency deviation. It is a relative displacement of the carrier frequency in respect to its unmodulated value. It is also the amount of change in the carrier frequency produced by the signal. Frequency deviation in terms of hertz can be expressed as the product of the frequency deviation constant and the modulating signal peak voltage, wherein the maximum deviation occurs at the peak positive and the negative amplitudes of the modulating signal occurs at the peak negative. Second parameter that we need to consider is the FM modulation index. It is the ratio of deviation and the modulating signal frequency that determines the number of significant pair of sidebands in a power spectrum of a given FM signal. So let's say we have a frequency modulation that has a modulation index of 4, then we expect in terms of its frequency domain that the FM signal has 4 pairs of significant sidebands, where 4 sidebands for the lower part and another 4 sidebands for the upper part. The FM modulation index can be expressed as this equation, as the frequency deviation is divided by the modulating signal frequency. So we have an example on this. Determine the peak frequency deviation and modulation index for a frequency modulator with a deviation sensitivity of 15 kHz per volt and a modulating signal of 10 cosine 2 pi 5000 t. So we have the given values from the problem that the deviation sensitivity is 15 kHz per volt, and it's given its FM modulating signal, where we can describe that the peak modulating signal amplitude is 10 volts. Note that the formula for the peak frequency deviation is the product of the deviation sensitivity and the peak modulating signal amplitude, which we can express as 15 kHz per volt times 10 volts, where we get the peak frequency deviation of 1.5 kHz. To determine the modulation index, we just divide the frequency modulation or the modulating frequency of the given modulating signal, which is 5000 Hz. Hence, we get the modulation frequency for a frequency modulator given is 0.3. Another parameter that we need to consider is the deviation ratio. It is also known as the worst case scenario, the worst case modulation index rather. It is the ratio of deviation and the modulating signal frequency that determines the number of significant pair of sidebands in a power spectrum of a given FM signal. This parameter is equation to the maximum peak frequency deviation is divided by the maximum modulating signal frequency. So an example to this is, what is the deviation ratio of an FM signal if the maximum allowable deviation is 18 kHz and the maximum intelligence frequency is 4.5 kHz. So we have the given values which can express maximum allowable deviation of 18 kHz and the maximum intelligent frequency of 4.5 kHz. Note that the formula for deviation ratio is the maximum allowable deviation is divided by the maximum intelligent frequency, where we can express as 18 kHz over 4.5 kHz. Hence, the deviation ratio of an FM signal is 4. Another parameter that we need to consider is the FM percent modulation. It is the ratio of the frequency deviation actually produced to the maximum frequency deviation allowed by law stated in percent form. So an example to this is, the maximum allowed deviation of the FM sound signal in TV is 25 kHz. If the actual deviation is 10 kHz, what is the percent modulation? So we have the given that the maximum allowed deviation is 25 kHz and the actual deviation of 10 kHz. Note that the formula for the percent modulation is just the ratio times 100%. Hence, it is 10 kHz over 25 kHz times 100%. We get the modulation or the percentage modulation of the given FM sound signal of 40%. And the final parameter that we need to consider of an FM signal is the FM bandwidth. There are 4 requirements that we need to consider. The first one is the Carson's rule. It is a rule which is an approximation and gives transmission bandwidth that are slightly narrowed than the bandwidths. And it can be expressed as the twice of the sum of the modulating frequency and the frequency deviation, in which the bandwidth defines as approximately 98% of the total power in the modulated wave, and significant sidebands are considered greater than 2% of the carrier. Another requirement for the FM bandwidth is the narrowband FM, which is only occur when an FM system has a relatively low modulation index, where we can express as the twice of the modulating frequency. The opposite of it is the wideband FM, which only occurs when an FM system has a relatively high modulation index, in which we can express as the twice of the frequency deviation. And lastly, the fourth requirement, or the final requirement when it comes in FM bandwidth, is the practical bandwidth using Bessel function. The Bessel function determines the magnitudes and signs of the frequency component in the FM spectrum. Hence, the sidebands were governed by the given function that according to the order and the modulation index. As the modulation index increases, each sideband pair follows its own path of increasing and decreasing strength. Theoretically, the FM signal consists of a carrier and an infinite number of pair of sidebands, each preceded by J coefficients, but only those sidebands with significant amplitudes are transmitted. In determining its bandwidth using the Bessel function, it is expressed as the product of twice of the modulating frequency signal and the number of sidebands of an FM signal. So an example to this is, what is the bandwidth of an FM signal with a 5 kHz maximum frequency deviation and 2.5 kHz maximum modulating frequency? Since we have the given, and the question to this is to find its bandwidth. Since the maximum frequency deviation and the maximum modulating frequency is given, we will use the Carson's rule to determine the bandwidth of the given FM signal, which we can express as 2 times 5 kHz plus 2.5 kHz, which we give the bandwidth of an FM signal of 15 kHz. Now that we have discussed the FM parameters, we need also to discuss the matters on the PM parameters, which are the following: phase deviation, PM modulation index, and PM percent modulation. The first parameter we need to consider is the phase modulation, or the phase deviation rather, which is the relatively angular displacement of the carrier phase in radians in respect to the reference phase. The parameter can be described as the product of phase deviation constant in terms of Hertz per volt and the modulating signal peak voltage in terms of volt, which one can express as the given formula. However, when it comes to PM deviation index, it is just a phase deviation of the PM signal. So meaning, the PM modulation index is just the phase deviation of the PM signal. For the PM modulation index percent modulation rather, it is also similar to the AM and FM percent modulation, but the parameters are phase deviation and maximum phase deviation. So for the example number 5, an FM communications transmitter has a maximum frequency deviation of 5 kHz and a range of modulating frequencies from 300 Hz to 3 kHz. What is the maximum phase shift that it produces? So since we have the given values of frequency deviation of 5 kHz and its range of modulating frequencies, but since we need to determine its maximum phase shift, the modulating frequency must be at the minimum value because the phase shift is inversely proportional to the modulating frequency. And since we all know that the PM modulation index is the phase deviation of a PM signal, then we can express as the frequency deviation divided by the modulating frequency. Thus, 5 kHz over 300 Hz is equal to 16.6667, but since this is a phase shift, we need to consider the unit of rad. Therefore, the maximum phase shift that it produces is 16.6667 rad. And that would be all the concept of angle modulation.